Hey Geometry, let's work through Lesson 9, Perimeter and Area of Triangles in the Cartesian Plane. I know we've done this a few times, but we have a new method today, which is actually sort of fun and may show up on a standardized test in the future. First of all, let's do a little bit of review. Find the area of the shaded region. For the example on the left, the shaded region would be the area of the square minus the area of the triangle. The area of the square is 4 times 4, length times width, which is 16, and then the area of the triangle would be 1/2 base, which is 2, times height, which is also 2. 2 times 2 is 4, divided by 2 is 2. So if you subtract those, you get the area of the shaded region, which is 14 units squared. Here we have a circle with a rectangle on the inside. So if I do the area of the circle, it is pi r squared. The radius goes out to 3, so 9 pi. And then the area of the rectangle is length times width, 2 times 4, which is 8. So the area of the shaded region, excuse me, is 9 pi minus 8, and you can't simplify that any further. There's your review. Okay, let's look at the harder stuff, the stuff that we're learning today. So example 1. Consider a triangular region in the plane with vertices of 0, A, and B, or sorry, O, for the origin A and B. What is the perimeter of the triangular region? I sketched it in Desmos so I could see it better. Now, mind you, we really, actually, I think I can highlight in white. See how this works. Yeah, that'll work. Oh no, too close. Okay, we really don't care about the tails on our triangle. We only care about the actual triangle itself. So to do perimeter here, we're going to have to calculate the distance between A and B, the distance between A and O, and the distance between O and B. I'm going to push pause and do this. You guys know how to calculate distance, so you don't have to watch me do it. I'll show you my work though, so give me a few seconds. So the perimeter here is approximately 13.21 units. Okay, check my work. I think I did everything right. Yeah, I think so. Now the next question asks you what the area of the triangular region is. Now, if this were a right triangle, that would be easy to figure out. So my question is this triangle a right triangle? Let's do this. The square root of 29 is my largest number, so I'm going to use the Pythagorean theorem to check. So 5 squared plus the square root of 8 squared, does that equal the square root of 29 squared? So I have 25, sorry, that's messy, 25 plus 8. Does that equal 29? No, it doesn't. So it is not a right triangle, correct? All right, so when we need to calculate area, that's going to be a little harder. Let's figure out how we do it. So consider the triangular region, same one as the last slide. What is the area of the triangular region? Well, if it were a right triangle, it'd be super simple, but it's not. What do we need to know for the area of a triangle? I have area equals 1/2 base times height. I mean, we could find a base and do like, okay, here's my altitude, what's my distance there, but we're not going to do that either. Let's think about how we found the area of the shaded regions in the previous, in the beginning slide, the first slide. So if I build a rectangle around this triangle, I now have a shaded region. Now if I look at my shaded region, I can pretty easily calculate the area of each shaded triangle and subtract it from the area of the rectangle, right? Yeah, we can definitely do that. First of all, let's do the area of the rectangle. That's going to be 5 by 4 equals 20 units squared. Now I can do the area of the triangles. So area of triangle 1 is 1/2. Base is 1, 2, 3. Height is 1, 2, 3, 4. So that's 12, 6, and then the area of triangle 2 is 1/2, 1, 2, 1, 2. Is 2, and then the area of triangle 3 is 1/2. Base goes 5 times height is 2. So 10 divided by 2 is 5. So I can do the area of the rectangle minus the area of all of the shaded triangles. This is 8. 8 plus 5 is 13. 20 minus 13 is 7 units squared. That was easy, wasn't it? We got a great answer. It's a correct answer. It wasn't that difficult to do. Now my next question is, can we develop a formula for the area of any triangle that has one vertex at the origin and the other two somewhere else, right? So we're going to try to develop a formula so that we can calculate area of any triangle that has a vertex at the origin and 2 other points in another place. So let's look at it. A general formula, okay, as shown. So what do? So what's the area of the rectangle of this one? I've got x1 times y2, right? Okay, now 1, 2, 3. How about the area of triangle 1? 1/2 base, which is this length, that's x2, times height, which is y2. The next triangle is 1/2 this distance. It's going to be x1 minus x2, because this whole thing is x1, times my height, which is y2 minus y1. And then the area of triangle 3, 1/2 x1 times y1. Okay, those are my 3 triangles and my rectangle. Now, just like the last example, I'm not doing anything crazy here. I'm just using letters instead of numbers, which makes math not as fun, right? We like the numbers. Now, I can do my whole subtraction thing, so I get the area of the rectangle minus the area of each triangle. Triangle 1, triangle 2, triangle 3. So that gives me x1, y2, which is right there, equals area of triangle 1, sorry, not equals, minus area of triangle 1 minus area of triangle 2 minus area of triangle 3. Crazy, huh? All right, this is the area of the triangle in between. I'm gonna get a next slide and do some math. Hold on. Alright, I copied the equation down. All I've done so far is expanded this right here. I've got two binomials, so I FOILed it. First, outer, inner, last. Push pause and check it out. You'll see that's all I did right here. And then the next thing I did is I took this negative 1/2 and I distributed it all the way through. Now I'm going to collect like terms, or hopefully cancel things out. Here I have a negative 1/2 x2 y2, looking, positive 1/2 x2 y2. These guys are gone. Cool? Let's see, the next thing I have is, up here I have a negative 1/2 x1 y1, positive 1/2 x1 y1. Later. What else do I have? Alright, I'm going to rewrite it. A equals x1 y2 minus 1/2 x1 y2. Ooh, I see that. Minus 1/2 x2 y1. Let's simplify that. Here, this has a coefficient of 1 outside of it, so that would give me a negative 1/2. Because it's, no, positive. 1 minus 1/2 is a positive 1/2. So 1/2 x1 y2 minus 1/2 x2 y1. So x1 y2 minus x2 y1. We did it. We got it. That's our general equation. General equation for the area of a triangle in the coordinate plane with one vertex at the origin. Cool. Alright, let's test it with this one. I don't know if you can still see the points underneath there. If you still see the points, we can go ahead and try it. I'm going to go ahead and move, or grab some points and try the math. I haven't done this yet. So I have x1, which is 3, times y2, which is 2, minus x2, 5, y1, 4. So this right here is 6 minus, well, I'm negative 6 minus 20, which is negative 14, which gives me a negative 7. Negative. So something I haven't told you yet, and I used this example as a learning lesson, we have to order our points in a counterclockwise way. So if I start at the origin, and I go that way, back to the origin, it always works. So this would be my first points, and this would be my second points, and let's try it again. So area equals 1/2 x1. I could hardly see underneath there. That would be a 5 y2 minus x2 y1. So 20 minus 6, 1/2 of 14 is in fact a positive 7 units squared. So remember the counterclockwise rule, okay? It works. Okay, next part in your classwork. It does work for this triangle. I just have to, again, order everything in the counterclockwise direction, and the answers work great. So let's try a few. We've got some exercises, and then I have one more thing to teach you, so don't think the exercises and then we're done. We'll keep going. Oh, we already did this. Okay, remember counterclockwise. Alright, so find the area of the triangles with vertices listed, first by finding the area of the rectangle enclosing the triangle and subtracting the area of the surrounding triangles, then by using the formula. We're going for this one, okay? Just because. Okay, here we go. I just sketched them out really quick. I wanted to make sure I knew which way to go counterclockwise and what I would be doing. So let's go ahead and try it. It's 1/2 x1 y2 x1 y2 minus x2 y1. Okay, 24 minus 5. 9.5 units squared. Okay, here we have area 1/2 x1 y2. We start with a first, so x1 y2 minus x2 y1. So I get 18 plus 4. 1/2 of that is 11 units squared. Okay, I'm sure you don't have to just sketch these each time, but I'm just making sure. So we're going to do 5 times 6 minus -3 times -2. Gives me 30 minus 6, careful on those signs there, which is 24. Half of that is 12 units square. Awesome. Okay, we're not done yet. I know your classwork packet is about done, but I need to show you something called the shoestring. It's pretty cool. Shoelace formula. Whew. I knew that wasn't right. Hopefully that makes you guys smile, not frown. Shoelace formula. Okay, so hold your horses. Don't leave me yet. All right, before we get to that, I just want to show you one thing. Question is, in example 1, we saw that the area of the triangle with vertices of 0, 0, so O, A, and B, it was our first example where our triangle was at the origin and it had an area of 7 square units. Can you find the area of a triangle with these vertices? If you compare these vertices to those vertices, you can see that it's just a translated triangle, and I just translated it to the origin. Well, actually, between here and there, I translated it away from the origin. So I, added 10, subtracted 12, added 10, subtracted 12, added 10, subtracted 12 for each of the values. So it works out the same. I can still use the 1/2 x1 y2 minus x2 y1 to find my area. If I translate one point to the origin, works great. Cool? Okay, that's what I wanted to show you with this example. Now we're going to look at the shoelace formula. All right. All right, let's start talking about the shoelace formula. I have a triangle. It is not set at the origin, and I would like to be able to calculate the area of it. So I'm going to translate point C to the origin. So I'm going to subtract x sub 3, y sub 3. All right, there we go. I just translated point C to the origin, right? So let's use our formula, our shoelace formula, and write down what the area would be. So area equals 1/2 x1, which is now x1 minus x3, y2 minus y3, so x1, y2 minus x2, y1. So x2, y1. Double check my work. This would be x2, y1. And I think I've got everything. So I'm going to simplify, FOIL, etc. One second. So I'm going to FOIL this and FOIL this just to show you how everything ends up. But I'm going to do that offline. Be right back. Alright, if you look over here, I FOILed it. So x1, y2 minus x1, y3 minus x3, y2 plus x3, y3. Then I FOILed this. x2, y1 minus x2, y3 minus x3, y1 plus x3, y3. Okay? So it's a minus in between here. So I'm going to distribute that negative, take out this parenthesis, and distribute that negative. So I have minus, plus, plus, and this would be a minus. Now let's see if we can collect like terms. I'm looking for anything that's the same. x3, y2? No. x3, y3? Yes. I think that's it. Bummer. Only one like term. That sort of stinks. All right, let's write our answer. Let's write our answer. I'm gonna do this live so you can see how I collect everything, and I'll show you how it makes sense when I'm done. So x1, y2. I'm gonna cross them off as I go too, and then x2, y3 plus, then x3, y1 and then we're going to go minus y1, x2 and then minus y2, x3. I would write this down if I were you, and then minus y3, x1. I know I flipped the order, and it'll make sense in a second. So this is called the shoelace formula, and I'll show you using this little diagram on the next slide. Okay, so write this down. I'm going to copy a few things over so I can show you a pattern that will hopefully make sense to you. All right, to remember the pattern, as a reminder, we need to order the points in a counterclockwise fashion, right? So let's walk around the triangle and come up with our formula, okay? So we're walking around the triangle in a clockwise fashion, and we can follow this pattern here as I go. I've just labeled them x1, y1, x2, y2, x3, y3. So we see here, I have x1, oh, it's not labeled, x2, y2. I have x1 times y2, x2 times y3, x3 times y1. And that's what we have right here, and those are all plus. So you can follow it here, or you can follow it up here. I'm going to do it one more time. x1 times y2, x2 times y3, x3 times y1. And those are all the pluses. Then I'm going to go again. Now I'm going with the y terms. y1, so I'm minus y1 times x2, minus y2 times x3, minus y3 times x1. And we have the whole thing with 3 points. Okay, I'm going to go through an example with actual numbers in a second, but they call this just the shoelace formula because we're really sort of lacing our shoes. And I mean, I've seen some standardized tests that talk about the shoelace formula, which is just crazy, but it's a fun way to figure out areas of triangles with less work than, you know, what we'd have to do before is draw a rectangle or a square around it, find the area of all of these, and subtract it from the area of the rectangle to find the area of what's left. Okay, so it's just another way to work things. Okay, let me get another example for us to work through with actual points. All right, let's go through this using the shoelace formula. I always want to call it the shoestring formula. It is the shoelace formula. So I'm going to walk around the triangle counterclockwise. I've labeled it. If you notice, they made a mistake up here with their labels, so I fixed it in red. So let's go ahead and try it. I'm going to go around once doing pluses and go around the second time doing minuses. So first, here I'm going to go x1 times y2. So 4 times 3 plus x2 times y3, negative 2 times negative 2, plus x3y1. So x3y1 would be negative 1 times 3. Cool. Now let's go again, except we're subtracting, minus, and here we're going y1 x2, so y1 x2, 3 times negative 2, y2 x3 minus 3 times negative 1, and then y3 x1, negative 2 times 4. Awesome. Let's do our multiplication. PEMDAS tells us we have 12 plus 4 minus 3 minus a negative 6 minus a negative 3 minus a negative 8. That's sort of messy. I've got a plus and a plus and a plus. So that gives me 1/2. 12 plus 4 is 16, minus 3 is 13, plus 6 is 19, plus 3 is 22, so 19, 20, 21, 22, plus 8 is 30, equals 15. Cool? Alright, honestly with more practice it gets easier, you have to trust me on that. Question for you though. Do you think this will work for figures with more than 3 vertices? Yes, it will, and I think we have one problem like that in your homework. But, cool. That's it. That's the shoelace formula. And that's the end of your lesson.